Gentlemen have come all the way from China to talk to you guys about breaking Google Home and exploiting it with SQLite. Let's give them a gigantic round of applause. Have a great time. Smile. I'm going to take pictures. Have fun.
Thank you. Hello, everyone. Thank you for coming. We are very excited to share our research at DevCon 27. The title of our talk today is Breaking Google Home, Explore It with SQLite Magellan Vulnerability. First, let me introduce my teammates and myself. We are senior security research at TensorBlade team, and this is my teammate Qian Wenxiang. Now he is focusing on browser security and IoT security, and this is Ni Yuxiang. He is focusing on mobile security and IoT security. And my name is Wu Huiyu. I'm a bug hunter and a geek runner. I also speaker for DevCon, Hacking Boss, and POC. Next, I will introduce the TensorBlade team. Our team was founded by Tencent Security Platform Department at 2017. And now, we are focusing on the security research in areas such as AI, IoT devices, mobile devices, cloud, and blockchain. In the past years, we have reported more than 200 security vulnerabilities to many companies, such as Google, Apple, Amazon, Microsoft, and so on. Last year, we shared how to break Amazon Echo at the DevCon 26, so we can again this year. And you can connect us at blade.tencent.com. Okay. Next, let's take a brief look at the outline. First, we will introduce the attack surface of Google Home smart speaker. Then, we will share the details on how to find and explore SQLite and Curl. Finally, we will summarize our research. Okay, let's start with the first part. Smart speakers are the most popular smart home devices of the past 3 years. Amazon, Google, and some Chinese companies are the main players in this field. In the fourth quarter of 2018, Amazon and Google's market share has been very similar. After we shared how to break Amazon Echo and Xiaomi AI speaker in DevCon 26, we began to study the security of Google Home smart speaker. The Google Home family includes 4 devices, all of which have similar hardware. We choose the best-selling Google Home Mini as the main test devices. The first part is about hardware analysis. We found that the Google Home Mini used the Marvell's CPU and Toshiba's flash chip, but we did not find any debugging and flashing interface. So, we can only choose to extract firmware directly from the flash chip. Similar to the Amazon Echo, we first use a heat gun to solder the chip from the board. By analyzing the datasheet of the chip, we found a test circuit of BGA67 chip. And the difference is that the pins of BGA67 chip are very thin. So we have not found an adapter that can connect the test circuit to the programmer. So we designed a new adapter. Its main function is to explore the pins of the test circuit to a notch pitch. The pins so that we can easily connect the chip to the programmer. And this is the finished product that we finally produced. We connect it to the RT908H programmer, which is a universal programmer that supports reading and writing most of flash chips. Finally, we got the RAM image data in Google Home's flash chip. We also need to parse the OOB data and ECC trigger bits according to the specification in the datasheet and extract the complete system firmware. By analyzing the system files, you can know that Google Home is using a NAT Chromium OS. The main functions are implemented by the Chromium OS, by the Chromium browser, and the update speed will be a little slower than the Chrome browser. Okay, my part ends here, and my teammate Liu Xiang will continue to share the next part.
Thanks for your introductions. Next, let's introduce the security overviews of Google Home. Firstly, let's look at the security overviews of Google Home. On the OTA mechanisms, the firmware's related resource of Google Home is open to public. These resources include bootloader, kernels, and related binaries programs, and some even has samples. Google Home uses the HTTP request to download the firmwares. We can also simulate the request for device updates. The latest OTA package can be obtained by the curl command in the pictures below. So we can easily to get the firmware and then try to analyze the firmware. Through the analysis of firmwares and related resources, we believe that the security mechanism adopted by Google Home is worth learning. About length, enabling security boot on IoT devices is a good example. The bootloader, boot images, system images is protected by the security mechanism throughout the boot process. The details as follows. The bootloader and boot images use the same signatures methods and are interpolated with SHAs and ISA signatures. The bootloader thinks that there is no logic to provide unlocking. In addition, Google Home also performs integrity verifications on system image. Let's look at the main programs in the firmwares. The firmware has memory directories as shown in these pictures. That contains a main program called cat shell. The program just like Chrome, so its program is protected by sandbox. On Chrome OS, the sandbox mechanisms mainly include setReady, your namespace, and sitcom BPF. In addition, the system also enables ASLRs, and the cat shells also add NX and stack canaries. Next, we will introduce the attack surface on Google Home. Combined with existing security research and our testings, Google Home's attack surface includes the following four aspects. Google Home has multiple port opens. One of the port is the A008 is the HTTP servers. We can control some basic operations of Google Home through these ports in the LAN. There is also a port of A009. The port is the target of our attacks using the CAT protocol. We will describe in the following sections. The wireless protocol is also an attack surface. Google Home used the malware chip. Some idea about malware Wi-Fi and BLE firmware attack can be tried. It is also possible to try to find the vulnerabilities of the bootloaders and let it load malicious firmware. Finally, we can try to find another hardware interface. In these sections, we will show you how to extend the attack surface of Google Home. First, let's introduce the basic knowledge about the CAT protocol. Google allows developers to develop CAT apps and publish it to App Store. In general, the CAT app includes senders and receivers. Sender devices may be mobile devices or PC running Chrome. Receiver is Google's IoT devices such as Google Home. The entire architecture is as follows. The user accesses the sender application URL, and the sender application uses the CAT protocol to find the receivers in the LAN. When the receiver is discovered, the sender application will communicate directly with the URLs, with the reader applications on the receivers. with the CAST protocol. In detail, the Google Homes will prove the URL of each receiver application according to the CAST APP ID and accept the receiver application through the Chrome renders. After our attempt, we found that CAST protocol will have the following security risk, including the CAST APP can be any web page. The CAST APP is the APP store may be malicious, and senders can directly trigger a CAST protocol, which may even require no user interaction. Based on this security risk, we can gather an attack on a Google Home into an attack on a browser. Let's take a look at some special states. The attackers is registered as the CAST developers. CAST application can be developed and distributed. When you publish an application, you need to specify CAST receiver URLs. However, Google does not audio link or CAST apps. Hence, we can specify it as a web page in any context. Remotely trigger the Google Home to access any web page. If the attackers and the Google Homes are in the land, the attackers can also send a CAST protocol such as the launch app's request. This request will directly trigger the Google Home accept to the CAST receiver URL. To make matters worse, if the routers in the victim's homes turn on the UPnP port forwarding, the attacker can also complete the remote silent attacks on the internet. The attackers modify the CAST receiver URL web page to a malicious page. Lens Google Homes may assist in renders after visiting the page. So now we only need to Chrome assist vulnerability to exploit Google Homes. Now, Wenxiang will introduce Magellan and other vulnerabilities.
Okay, thank you for the introduction. Now I will continue with part 3, fuzzing and manual auditing SQLite and curl. First, why do I audit these two libraries? Because third-party libraries are always sweet. They have less code and focused functions, and almost every device has them installed. And the most important thing is Google Home or Google Chrome are using them too. Before introducing the code audit part, I would like to mention some previous researches. First, Michael Zawitsky's fuzzing has significantly improved the SQLite's quality. And then there's a talk on Black Hat in 2017, which also explains the idea of exploiting SQLite. After that, there doesn't seem to be a lot of news about the vulnerabilities of SQLite, but we have found some. In the next part, we will introduce the code auditing and the exploiting of Magellan, which is a set of vulnerabilities in SQLite, and Diaz, which is a set of vulnerabilities in curl. The Chromium project comes with a father for SQLite. We have made some simple changes to it, such as adding some syntax-based Fuzz. When we look back, we found that there was a lot of crash files generated. However, these test cases can only trigger empty pointer dereferencing. One of these test crashes is caused by duplicate primary keys, and when I was bugging, I typed the first 3 create table statements to see what was going on in memory. However, I was surprised to find that the .tables command shows 6 tables. The question is, what those content segdir segments stand for? The SQLite manual shows that the tables are called shadow tables. There are 5 types of shadow tables. Content segdir segments are for FTS 3 or 4, and state and doc size are FTS 4 only. However, because of those tables are treated like standard tables, you can create corresponding state and doc size table, even you are operating on an FTS 3 table. You can create state and doc size by simple create a table statement, because SQLite itself is doing this too. And FTS 3 and 4 is sharing some code, which means state and doc size might change the code flow in some conditions. For example, one of our exploits are simulating an FTS4 table on FTS3 environment. This is useful because some software like Chromium use only FTS3 and explicitly disabled FTS4. This would extend the attack surface by entering some code branch that should never be entered. The shadow table is used as a container to store the content of the full text search metadata. What is shown on this slide is the definition and meaning of each shadow table. We can see that almost every shadow table has a field of type blob. That's because to support full text queries, FTS maintains an inverted index that maps from each unique term or word that appears in the dataset to the locations in which it appears within the table contents. It is complicated, but all we know is that compared to other fields, those blobs may have some important influence on FTS queries. In SQLite, the raw binary data is typically represented in the form of X, single quotation mark, and hexadecimal numbers. However, the blobs here are binary data to represent the entire B tree. Since it represents such a complex structure, is it possible to create a memory corruption vulnerability by destroying the data of the structure? Let's read about the document of the serialized data structure first. You can check the SQLite manual to easily get the definition. I will show you a simplified version so you can understand what I'm modifying when I'm trying to exploit them. Basically, I'm modifying the bytes with different functional sections to mislead the code flow. The first, segment B tree leaf nodes. The first term stored on each node, which is term 1 in the figure above, is stored verbatim. Each subsequent term is prefix compressed with respect to its predecessor. Interior nodes, non-leaf nodes, have different structure. And then the docklist format. A docklist consists of an array of 64-bit signed integers, serialized using the FTS var_int format. Each docklist entry is made up of a series of 2 or more integers as follows. 1, the doc ID value, and 2, the 0 or more term offset lists. In general, those blobs are just serialized B tree data. When the SQLite wants to perform operations on those tables, it will simply deserialize or parse those blobs and get a complete B tree. Then I have found some problems. The problems are mainly treated to merge and match because they are deeply related to the B tree. 2 of them merge the node of the tree, and other is to traverse the nodes of the tree to try to find the matched content. Also, the last one is the crash I mentioned before. It was that brought this series of problems into my attention. And software must enable FTS3 support and support external SQL query to trigger these problems. Okay, the first one, 20346, which is also the main vulnerability we use later to exploit Google Home. It requires a lot of complex preconditions. That is, we have to carefully construct a lot of tables and content. But once the preconditions are met, vulnerability exploitation will be very simple and stable. The vulnerability is located in the function FTS3 append to node. It can be triggered with a special semantic, the merge equals 1,2, which means the level to be merged. As you can see, this function will try to append a node to another. The node is stored in the blob, so this function and up function will first pass in the B tree and then get the start position and the length of binary data of the node that will be processed. And last, perform the memory copy operation to copy them into a new blob that represents the new tree. Okay, let's go to its caller function, truncate node. It will get the binary offset and length from the blob data that will describe the node being processed. Then the node information is returned in a reader object passed to the vulnerable FTS3 append to node. To control the memory copy in append to node, we need to control a doc list and n doc list, which is returned from node reader next. The a doc list is the source of the char pointer to the blob data, and n doc list is the node size, which are second and third parameter of memory copy, respectively. To control them is not a difficult thing. Let's read the code, then you will know why I'm saying that is easy. To save the space of storing an integer, SQLite uses a variant integer algorithm. You can just consider fs_get_variant32 as a function to convert a bunch of bytes into an integer. It will store the result in n suffix. Then it moves the current cursor by adding the content of bytes and read it to I off. The data for a node is stored as a length, followed by corresponding data with exactly size of length. Normally, they should appear in pairs, but we can modify the blob to make the end of the blob boundary has only the length field but no data field. Okay, let's go to the append to node. Since in the last step, a dog list and n dog list is controlled, we can now overflow the buffer of p node A in line 310, or we can copy some raw memory data to it, as long as it does not exceed the aligned value. Then we can query the new table to get the leaked raw memory. By setting up adjacent tables, we can overflow the function pointers of the table very accurately to exploit a code execution. And here's another one, 506 in function scan into real node, and the precondition of this one is rather simpler. All you need to do is modify the shadow table, set a node in secdir to non-root node. You can change the blob data to change the code flow. Query the modified table by keyword match. Then the code will scan every node inside the B tree. Then the code will trigger memory corruption. Because it has many constrained conditions, it was considered to be very hard to exploit. But this one is exploitable anyway. You can check the wonderful write-up by a Korean researcher named Qian. And last, 20505. This one is very like to a combination of the previous two. The vulnerable function is segregator next. You can modify the shadow table and mislead the code flow. All these three vulnerabilities can be modified to leak raw memories, so we can also use this to leak address of, for example, functions, structures, global variables, constant variables to bypass the ASLR. And here's another one, LabCurl. Our target is remote code execution, but LabCurl has already been used by a lot of users, and their code iterates very quickly too. To find a vulnerable function, here are some guidelines for finding problems by reading the code quickly. The first, find the big functions. Most functions with a lot of lines is not recommended in software engineering, and functions that are too long should be refactored into shorter function fragments. Usually, such a large function is difficult to test, and there will be a lot of attack surface. And most of the functions enabled in LabCurl is related to remote interactions and communicate with the remote server more than once. After carefully sifting through the protocols, we confirmed that NTLM over HTTP was what we wanted to test. And here are those problems we have found in LabCurl. We named them as DS, name of another famous navigator. The first one, 890, is a vulnerability in NTLM type 2 message. It can leak at most 64 kilobytes client memory per request to attacker. The result is very like to the Heartbleed, but is the client version. And the second one, 3822, is a vulnerability in type 3 message. It will result in a stack buffer overflow. LabCurl also wrote this in his blog and thought it's a very bad security issue. Okay, let me show you how this happened. The first one, the vulnerable function is in decode type 2 target. It reads a 32-bit integer from the type 2 message header. Then we know we can set target info offset with a larger value and target info length to a graphic value, which if you add them together, an integer overflow will happen. The overflow result is very small and will pass the check in line 185. And next, memory copy will copy data out of bounds. For example, if we use the value above, it will actually copy data from the front of variable buffer in 32-bit environment. And then the data will be sent to the attacker in type 3 message, leaking maximum 64 kilobytes data per request to the attacker. And let's go to 3822. This vulnerability is located in a big function named curl_create NTLM type 3 message. In the beginning, this function declares a lot of variable on stack memory. The NTLM buffer is a big buffer which has around 4 kilobyte memory. Then the function tries to read NT response length from the type 2 response, which is sent from the server. Attack could return a value bigger than the buffer size to client. And next, in line 779, this check should check if the size of the data is bigger than NTLM buff's remaining size. But the inexplicit unsigned cast prevents the check from operating correctly. This check compares two unsigned variables and a Markov NTLM buff size, which simply defines a number, 1024. But this value is a signed integer in the view of compiler. When unsigned and signed are compared in the same place, some of them must be casted in order to compare correctly. And this is a problem. The compiler prefers to convert signed to unsigned numbers. So if we have NT response length greater than the NTLM buff size, the result will be a large unsigned number. And it is, of course, bigger than the remaining size, will pass the check. In line 7H1, because NT response length is bigger than the remaining size of NTLM buff, hence here will be a stack buffer overflow. When the code triggers a stack buffer overflow, the overflowed variant is in the middle of a lot of stack variables. Although the program may have stack cookies, an attacker could choose not to overflow that mesh bytes, but instead override stack variants and control the flow of the code. I have marked the position where it triggers the buffer overflow. You can see in this big function, there are almost 18 lines after it. And many of them are operating heap or stack memory, and the operating is based on the value of those stack variables. That's the reason why I say big function is never a good coding practice. Okay, my part is done, and Wenxiang will go ahead to introduce how to exploit.
Thank you for my partner's introductions. Now, let's review the following vulnerabilities. The keys to the vulnerability trigger is how to use the insert state to control the variables used by our memory copy function, include pnode A, pnode N, and a.list and .list. The insert data is as follows. First, the entire data is stored in the buffer of pnode A. We can control the size of the pnode A buffers by modifying the length of the insert state. In heap functions, we are able to allow pnode A to the appreciate areas to cover the target memory. In this state, the orange colors indicate that the size of pnode N and n.list, which is int type. N.list is used to control the length to be overflow. Pnode N, which is the offset of the overwritten memory areas. The green part is the a.list data, which can be used for OOB read or OOB write. The next sessions, we will introduce the ideas of using these vulnerabilities. We expect to find function pointers that can be used on a heap. When creating FTS3 tables, the tokenizer is created by default. And the tokenizer default is simple tokenizers. As shown in the following pictures, simple tokenizer is a structure on the heap where is members base points to the SQL trees tokenizer structures. The members P models or the SQLite trees tokenizer structure points to the tokenizer models. The tokenizer models contain some interesting function, callback functions, such as the create xopen amount length. When inserting the FTS tree tables, the xopen callback functions will be triggers. If a function address of xopens can be modified to the attributes address, the PCs can be hijacked. How to use the variables functions pointers for PC hijacking? Here's two conditions need to be met. The first, after his overflow is necessary to be able to operate the FTH3 tables. In addition, when hijacking needs to be complete before the memory is released, otherwise the crash will be interrupted. By analyzing the logical of memory copy to freeze, we found an interesting function which performs a SQL update operation before releasing the memory, as shown in the blue tag code. Finally, we use the SQL triggers to perform the FTH3 table insert operation before the SQL update operations and free memories. Thus, triggering the xopen callback functions so that the PCs can be hijacked. The next step is to make a memory layout. The SQL logical of the castle shell use tmalloc. A feasible memory layout idea is as follows. The first, by creating multiple FTH3 tables, we will create multiple simple tokenizer structures. Drop the previous created FTH3 tables at the appreciate times. The simple tokenizer structures will be free. The residing payloads of the same size as simple tokenizers, it has the high probabilities that payloads will be allowed to the previous release simple tokenizer structures. So our payloads has a greater chance of operating the simple tokenizer structures of existing FTH3 tables. With the SQL triggers that perform the operations of FTH3 tables before the free, there is a chance that the tokenizer model callback functions will be triggered to hijack the PC. When we have the ability to hijack the PCs and control the R0 registers, we only need to be able to list information and bypass ASLRs. The previous sections also introduced, we can try to adjust the undoubted pin node A and list memory after heap. We need to disclose the following two types of address. Linking the address of castle shells based on this address and offsets, calculate the required RP gadgets. Leading the address of the last heap according to this address and offsets, the probabilities of calculating the address of the heap split. The latest is the heap splits and RPs. After these three steps, we can access in Google Home's renders. Castle Shell is a large binary program that contains many of the available RP gadgets. So the RP gadgets used Castle Shell is more stable and convenient. In the pictures on the right, the red lines mark the heap split units, which face tokenizer models and RP gadget. The X create X open address in the face tokenizer model structures will be assigned the state pivot address. The blue line marks our face simple structure of tokenizer structures. When the FTH3 tables operate can be triggered, SQLite will get a malicious X open through the structures of simple tokenizers and then RC. Above is the screenshot of our RC in castle shells. The read blocks on the left show that the register we can control. That they are R0, R11. The function address is read from the R11s and finally go to BLX. Then, as a result, we have been able to hijack the PC. The image on the right show the results of our shell codes. We execute JavaScript codes for fetch URLs and navigators app name in the exp.html codes. Normally, navigators app name is read-only and is next skip, but our shell codes change the app name to AAA. Let's look at some actual attack scenes. There are 3 types of attack vectors that attack Google Homes remotely. First, the attacker is located in the LAN. The attacker sends the launch app ID 1 command through a CAT protocol, and Google Homes will pull the leak.html on the application stop, app stops according to the app ID and load it. At these times, the leak data can be obtained by the attackers. The second, the attacker sends the launch app ID tools command Google Homes loads exp.html, so that the RC happen. The entire process does not require user interaction. In the other 2 sense, you don't need to be on a send lens to start the attacks. The attacker indexes the victims to access the URLs of the sender application, and we can scan the networks on the routers that if the routers have the UPnP forwardings, we can try to launch remote attacks on the internet. Conclusion. Here is the timelines of the Magellan. We have report length in November and is quickly fixed by SQLite and Curl. In the December, Google decided to get us a total 10,000 rewards for the batch of vulnerabilities, and they have enhancements. There is the defense in diff flag, this allowing modifying shadow tables from untrusted source. For backwards compatibility, is default off in SQLite. So if you are using SQLite with FTS, you may want to enable this one to prevent the attacker from modifying your shadow table. But the good news is default on in Chrome from commit in the last November. Here is the timelines of DS. These quickly fixed and released by lab crews in 2 weeks. Also, we have noted the censor to urge vendors disable the vulnerable FTA trees of Web SQL before the patch come out, if they don't use these features. And we have notified the security teams of Apple, Intel, Facebook, and Microsoft about how to fix the program and how to mitigate the threats in some of their products. The other one is the security advice. The ones enhance your systems with the newest available defense in diff mechanism in a time. The tools keep your the third pass libraries up to date. 3. Improve the qualities of security auditing and testing of the third-party libraries. 4. Introduce security specifications into the developments and testings. Thank you.